As we look more at an ELF file content, we'll need to keep in mind the two different ways of referencing locations, referencing information from one part of an ELF file to another. One of them is to use an offset within the file to say where a segment starts or something like that. And that'll be reflected in the C structures as a type, as a reference of type ELF64 off. Right? When we copy the whole file into memory, that offset will correspond to an offset from the pointer that's the start of the copy. The other way that an ELF file will refer to different things in the file is through an ELF64 address. Right? And this address is the address that would be used if we were actually running this program. Right? And that's completely different than the address that might be used when we've copied the file into memory. For example, we saw that text was at a particular offset in the file, but when it was running, the machine code for a.out was put at a different location, at a particular address. It was 400, or something like that. Right? So the thing to understand is that even in the file format, sometimes other parts of the file are referenced by an offset, and sometimes other parts are referenced by an address that has to be correlated with some other information in the file. Right? In particular, program headers, if you're using the segment view, or section headers, they provide the information of how to go between an offset and the address that will be used at runtime. Let's look at a concrete example. So here I've got a program that has an initialized array A, it has a read-only array B, and it has an uninitialized array C. We're going to print the addresses of A, B, C, and also print the address of main, and see how that relates to what the ELF file had. So let's call this, let's call it example.c. Okay. So example.c has that code, gcc output to example of example.c. Let's use optimization just in case we end up looking at the machine code. Okay. So when we run example.c, it tells us for this particular run, the variable A was at that address, hex 601060. B was at this other address. C was at this other address. And the actual function main was at that particular address. If we use readelf on example, and let's see how the information in the ELF file corresponds to that running. So readelf says, yes, it's an executable file. If we want to know where A was, remember that A in example.c, spelled it, A was that initialized but writable variable A. So that is going to be in the data segment, in the segment view. Right? And our data segment description says it's at this place in the file, hex 1040. But when the program is run, we should expect to find all the things in the data segment at 601040. And we see that A is in fact just a little bit into that segment. The reason A is just not at the beginning is because we linked with the C library, or there could be other things that the C compiler adds. But A itself is in there somewhere. Where should we find B? B was this constant array with initialized values. So that should be in read-only data. And if we look for the RO data segment, let's see, I skipped, okay, there it is. It says that read-only data starts at hex 400600. That, again, is consistent with what we saw for B back here. Right, so B is in the read-only segment, as expected. And that leaves us with C. C was uninitialized data. So that can be in the BSS segment. There's no need to save 8 zeros in the file. So let's look for BSS. The BSS segment is hex 6010080. Again, that's consistent with the address that we have for C here. And finally, main, that's going to be code, so it should be in the text segment. Text segment is 400440, and yes, in fact, main is the very first thing that's in our text segment in this file. So that gives you an idea of how the ELF file records information that we saw being printed out at runtime. And in particular, A was in the data section because it's initialized. writable data, B was in the read-only data section, C was in the BSS section, and main was in the text section.